All right, here's our last video in section 8.1 on systems of equations. We've already talked about how to set up a system of equations from a word problem, how to double check if a solution is the correct solution to a system of equations. Now let's actually talk about solving a system of equations. Now there's actually three different ways to solve a system of equations. We can solve it by graphing, we can solve it by substitution, and we can solve it by elimination. In this video, we're going to talk about how to solve it by graphing. In 8.2, we'll talk about the other two methods of solving a system. Now, since the solution to the system is an ordered pair, a point that is true in both equations, it's actually really a point that is both on both graphs or the point where the two graphs intersect. So as soon as I can figure out where they intersect, that means it's a point not only on the first graph, but the second graph. So it's the solution to both graphs. So if I can graph it and figure out where they cross or intersect, I know that that point, that ordered pair, is the solution to the system of equations. So that's how we're going to solve it by graphing. Let's do a few examples. If you look at example number 4, it asks us to graph the system of equations on the grid below. So what we want to do is we want to graph both lines. Once we graph both lines, we want to figure out where they cross. The point that they cross is going to be our solution to the system. It's going to be the x and the y that work in both equations. Now, we've talked about graphing in a previous chapter, so let's go ahead and quickly review. If I were to give you the equation 2x plus y equals 5 and ask you to graph, what you're going to want to do first is get it to look like slope-intercept form. Remember y equals mx plus b? That's the easiest way to graph a line. So let's go ahead and do that for both equations first. So on my first equation, 2x plus y equals 5, if I want to get it to look like slope-intercept form, I have to get the y by itself. I want to get it to say y equals. So I'm going to go ahead and subtract the 2x from both sides. When I do that, I end up getting the linear equation, y equals negative 2x plus 5. Let's do the same thing for the other equation. In the second equation, let's go ahead and subtract the 2x from both sides. And you notice that I have a negative in front of my y, or a negative 1. So I want to make sure that I get rid of everything next to the y. So it just says y equals, not negative y equals. So let's go ahead and divide every term by negative 1. When I do that, I end up getting the equation y equals 2x minus 7. Since they now both look like slope-intercept form, I should be able to use their y-intercept and their slope in order to graph them. So let's do that now. So when I go to graph the first line, I know that the y-intercept is positive 5. So let's go up to positive 5 on the y-axis and make a dot. I know that my slope is negative 2, or I can say negative 2 over 1. That's my rise over run. So from my y-intercept, I'm going to go negative 2, so down 2, and I'm going to go positive 1, right 1. I'm going to do it again. Negative 2, positive 1. You can do it as many times as you need to make sure that your line is straight. You can go negative 2, positive 1. Or you could even go positive 2, negative 1. I can go up 2 and left 1. Either way, I'm going to get that same straight line. Okay, maybe not very straight, but all right, let's look at the second equation. In order to graph my second equation, it looks like the y-intercept on this one is negative 7. So I'm going to go down to the y-axis at negative 7 and make a dot. It looks like the slope on this one is 2, or 2 over 1. That means I'm going to move up 2, right 1, up 2, right 1, up 2, right 1. I'm going to continue doing that as many times as I need to make sure that I have a straight line. What do you notice about both of these lines? Don't they cross at this point right here? And so since they cross at that one point, that is the ordered pair, the point that is true for both equations. So that means that's the solution to the system of equations. Well, what point is that? Well, it looks like it's over on the x3 and down on the y1. So that would be the point 3, negative 1. That's the solution to this system of equations. Remember, you can always double check that by taking the 3 and plugging into the x, and taking the negative 1 and plugging it into the y to make sure that it actually works. It'll take you a few seconds, but then you know you have 100% on that question. Let's do another one. Look at B. I want to solve by graphing. So what I'd like you to do is pause the video. I'd like you to take the first step by yourself and put both of these equations into slope-intercept form, y equals mx plus b. Practice that first, then come back with me, and then we'll graph them together. All right, for the first equation, I'm going to go ahead and add x to both sides. I ended up getting y equals x plus 5. Hopefully you did too. On the second equation, I'm going to go ahead and subtract 2x to both sides. That leaves me with the equation negative 2y equals negative 2x plus 10. Then I'm going to divide every single term by negative 2. When I do that, I got the equation y equals x minus 5. All right, now that we both have the same equations, let's go ahead and graph them. If you look at the first graph, the y-intercept is positive 5. So let's go up to the y-axis at positive 5 and make a dot. Now, what's the slope of this line? You notice that there is no number in front of the x. Well, there actually is. It's just invisible. Remember, there's an invisible 1. Or can I say that it's 1 over 1, so I have a rise and a run? That means I'm going to go up 1, right 1, up 1, right 1. And you can do it as many times as you need to, or you can go down 1, left 1, just making sure that you're as straight as possible so that your intersection is correct. If you're a little bit off and you start to go crooked, well, then your solution isn't actually going to be the correct solution. So just be careful with that. So I oftentimes make a lot more dots than I need to. All right, let's look at the second graph or second equation. Let's go ahead and graph it. It looks like on the second line, the y-intercept is negative 5. So I'm going to go down here to negative 5 on the y and make a dot. And it looks like my slope is also 1, positive 1 over positive 1. So let's go ahead and graph that. I'm going to go up 1, right 1, up 1, right 1, up 1, right 1, as many times as I need to make sure that my equation is straight or my line is straight. All right. Uh-oh. This one looks a little bit different than the first example, doesn't it? Remember, in the first example, we could figure out what the solution was by where they intersected. But on this one, where do these two lines intersect? Well, don't you notice that on both of these lines, it looks like they're parallel? They actually are parallel. Do you remember that when two lines have the same slope, they're going to be parallel? Well, as soon as I noticed that their slopes were going to be the same, we should have recognized that they were going to be parallel, and two parallel lines are never ever going to intersect. So unfortunately, on this equation or this system, there is no solution. There isn't going to be a time where these two equations touch or intersect, which means there isn't going to be a point on the first one and a point on the second one that are the same. So there's no solution to this system of equations. Now, we can still solve it by graphing, but as soon as we notice that they're parallel, we need to understand that there's no solution. All right, let's try one more here. Why don't you go ahead and put both of these equations into y equals mx plus b, maybe even graph both of these equations, and then catch up with me here in a second. So pause your video. Why don't you practice those few steps, and then we'll come back together, make sure you're on the right track. All right, for the first equation, it looks close to y equals mx plus b, but it looks like that right side is a little bit out of order. So I'm going to just write it in a different order. I'm going to write the negative x first and the positive 3 second, so that it looks a little bit more like y equals mx plus b. On my second equation, I'm going to go ahead and subtract 2x from both sides. I ended up getting the equation 2y equals negative 2x plus 6, and then I'm going to divide every single term by 2. I ended up with the equation y equals negative x plus 3. Hopefully you got the same thing I did. All right, did you graph it? It looks like the first equation has a y-intercept of 3, so let's go up to 3 and make a dot. It looks like the first equation has a slope of negative 1, or can I say negative 1 over positive 1? That means I'm going to go down 1 and right 1, down 1 and right 1, making sure that my slope is negative. I'm going to draw as straight as possible a line to connect all of those dots, and that's my first equation. All right, let's go ahead and graph my second equation. It looks like my second equation has a y-intercept of positive 3. It looks like my second equation has a slope of negative 1, or can I say negative 1 over 1? That means I'm going to go down 1, right 1. Down 1, right 1. You notice anything? And maybe you noticed it a lot sooner than I did. You notice that they're the same exact graph? Well, if to determine the solution means where they cross, where do these two lines cross or intersect? Where do they touch? Don't they actually touch all the time? Every single one of these points is true for both equations. So what does that mean the solution is? Well, doesn't it mean that on this system, there's an infinite number of solutions? Kind of interesting. So we've actually looked at three different types of examples of solutions to systems of equations. The first one had one solution because it intersected once, right, at the point 3, -1. The second example were two parallel lines. They're never going to cross, so there was no solution there. On the third example, they happen to be the same exact line, so they're going to touch all the time. Every single point is going to be a solution for both equations. We have infinite solutions here. So there's three different types of systems. You can still solve them by graphing, but as soon as you graph them, you've got to figure out where they touch or how many times they touch or intersect. All right, the last little thing we're going to talk about is some words we can use, vocabulary we can use when it has one solution, no solutions, or multiple solutions. Now, if you look at the three different pictures here, kind of the three examples that we just did, you notice that the first one has one solution. When it intersects once, then it is called a consistent independent solution. It's consistent because it has one solution and they're independent of each other. If they're parallel lines, like on the second one, then we say it's inconsistent. There's no solution, but they're still independent lines of each other, inconsistent and independent. If I have a line that happens to be the same exact line twice, then we say it's consistent and dependent. So if it has a solution, it is consistent. If it has one solution, it's independent. If it has lots of solutions, it's dependent. If it has no solution, it's inconsistent and independent. So can you go back up to example 4, A, B, and C, and can you go back through and label each of these with those vocabulary words? All right, on A, because it has one solution, remember it's consistent because it has a solution, and they're independent of each other. So consistent and independent. What about B? B had no solution. They were parallel lines. That means it's inconsistent, but they were still independent lines, two different lines. And on C, there was an infinite number of solutions because they were the same exact line. Now, because there was a solution, we can say it's consistent and they're dependent of each other. Whatever the first one is depends on whatever the second one is because they're the same exact line. Make sure you understand how to solve by graphing. You understand what the solution means when you graph it, and then you can label each of those answers with the correct vocabulary term.